Good morning and welcome to this rendition of Nano Explorations. It is my honor to introduce you to Albert Liu. Albert is a graduate student in a group of Professor Michael Strano. And in about 6 days from now, he'll be defending his PhD thesis. What you're about to see is a fraction of that thesis work, and I'm very excited to be able to hear it. So in a moment, I'll pass the stage to Albert. But for right now, I just want to remind you that if you have any questions for Albert, please either send them in chat or wait till the very end, and I will call upon you if you raise your hand so you can ask the questions directly. But with that being said, I noticed most of you already have muted yourself and turned off your videos. Thank you for doing that. That will increase the bandwidth for the rest of us. That being said, Albert, please take over.
Thank you, Vladimir, for that introduction and the invitation for giving this talk. It's a great pleasure of me to introduce this topic that I've been thinking about for, as a group, thinking about this for the past several years of this topic of colloidal electronics. And so let's get started. So what is colloidal electronics? It's obviously composed of two words, colloids and electronics. A colloidal system can be defined as microscopically dispersed particles suspended throughout another medium. For example, in that glass of milk that we drink every day, you can think of them as fatty protein colloids suspended in a beaker of water, for example. But colloidal suspensions can be stabilized in other forms of substance too. For example, in aerosol particles in air, and also in the solid phase. Colloidal systems are ubiquitous in nature. For example, in the ocean, we often have these phytoplanktons that swims around, which can be also treated as a colloidal suspension. The defining feature of a colloidal system is its characteristic mobility, right? Because the particles are suspended in the liquid, it can be moving around passively with the liquid medium that it's in. The electronics, on the other hand, requires no further introduction. It has literally infiltrated into every single aspect of our lives. And so to graft electronics onto a colloidal system into that colloidal form factor will naturally extend electronics into previously inaccessible locations and environments. And this will change the way we think about medical devices, environmental monitoring, as well as microscopic sensing in chemical manufacturing industry. So just to give you a length scale of the problem that we're dealing with here, right? So here's where our everyday autonomous electronic devices lie on this ruler. Basically, it's tens of centimeters in scale, on your cell phones, your laptops. And tremendous amount of progress has been made in terms of shrinking down these electronic devices into, for example, centimeter scale in these ingestible electronic systems that can go into our GI tract. And a serious effort led by Berkeley some 20 years ago have led to the development of this smart dust or motes that can go beyond 1 millimeter in its critical length and can be used for neural activity monitoring and so forth. Of course, I think the holy grail of the field is to think about the possibility of further shrinking electronic devices down to the length scale of, let's say, a human red blood cell, which enables us to put finally artificial electronic devices or artificial devices into the human circulatory system and all kinds of crazy other applications that is out there. So this is roughly where we'll be talking about today, roughly at this 10 micron regime, which is what we define colloidal electronics are lying at. Now, fundamental to this problem lies several challenges. You can think about energy management, you can think about information relay and communication. But the problem that I want to highlight today in this particular talk is a fabrication problem. How do we integrate nanoelectronic devices onto a colloidal form factor in a very energy efficient way to create energy efficient circuitry? So the material of choice that we have relied upon is two-dimensional materials. I think for this audience, I don't have to introduce two-dimensional materials except saying that depending on material composition and structure of this atomic lattice, you can have different electronic properties. right? So you have you can have free at your disposal a conductive material, a semiconductive material, or even an insulative material found in like hexagonal boronitride. On top of that, two-dimensional materials are also very, very flexible. So this atomic thinness allows them to be grafted onto essentially any surface that we can think about. So this is an attractive feature for our the guiding principle of our fabrication method. So here's the idea. If you take a layer of two-dimensional material or a circuit that you can pre-pattern out of a two-dimensional material and treat them as origami papers, and if you fold them around an already existing dumb colloidal particle, right? You can have the top and bottom layer, sort of fold them around this particle. And if you have a way to cut these 2D material around the edge of the particle, then practically you're making these microscopic dumplings that has this two-dimensional material skin, the electronic skin, and the some sort of polymeric core serving as structural support. Now the particle suddenly becomes like intelligent in that they have this electrical property that is brought forth by the 2D materials in the form of this like alien-like electronic dumpling. Now, I'll be the first one to admit that I love making dumplings. People who know me knows that. But making thousands of these dumplings one by one wouldn't be a lot of fun at this kind of microscopic length scale. So is there a way for us to scalably fabricate 2D material enveloped or grafted microscopic dumplings? Well, the answer actually lies in controlled fracturation of the two-dimensional materials. This is sort of like a weird concept when I first encountered it. You know, if you think about fracture, and it's the fracturation process of a brittle material, for example, glass, never really appeared to be controllable. It's almost always stochastic, right? I, on average, break one iPhone screen every year. The process never appears to be controllable to me. So how come we can control the fracturation of two-dimensional materials? It turns out this problem has been solved almost exactly 100 years ago by Alan Griffith. So he's sort of the founding father of modern fracture mechanics, and he has put forth this Griffith Theory to describe the fracturation process of any given material. So according to his theory, when you have a piece of material and you advance a crack within the material, that is going to expose new surface area within the material. So if you plot the overall system energy as a function of the crack length, you see that the surface energy scales linearly with the surface area that you expose, and hence it's linearly correlated with the crack length. At the same time, when breaking the material, the strain energy that is built up within the material will necessarily drop precipitously, actually. So if you sum up these two contributions to the total energy, you get this concave shape, with this vertex of the concave being this critical length scale that we call Griffith length. Now this is interesting because any crack, this theory predicts that any crack that is shorter than this Griffith length on the left-hand side of it will actually not grow, because further increase in the crack will increase system energy. On the other hand, if your crack length is on the right-hand side of the Griffith length, it will basically precipitously grow and the material will fail. Griffith then went on to calculate analytically what the Griffith length is a function of other different material parameters. Specifically, he has pointed out in this formula that the Griffith length scales inversely proportional to the square of the specific strain at a given location of the material. So this is interesting, meaning that increasing material strain, it gives us a tunable factor that we can use to control the length of the Griffith length, hence to control the breakability of a material. So how does that square when we look at two-dimensional materials? Here's a piece of graphene under TEM. As we all know, CVD grown or chemical vapor deposited graphene or other two-dimensional material always have these inherent grain boundaries or defects that is on the order of nanometer scale. So these defects can be seen here. And if we think about these defects as seed crack that exist within our material, I'll actually say that this seed crack that you see right now is shorter than the Griffith length, with the reason being that it actually is stable enough for us to take this TM image, right? So this seed crack has to be on the left-hand side of the Griffith length. Now consider the thought experiment. What would happen if I pull on this graph a little bit? If I pull on this piece of graphene a little bit, then your new, imagine that you're sitting at this cracked tip, the strain energy is going to increase. According to this formula, your Griffith length is going to drop. So if your new Griffith length now suddenly sits on the left-hand side of the same seed crack length, the material will actually fracture. So by controlling strain, you can control whether or the direction at which a crack will propagate. So here comes the question, can we control material fracture within the two-dimensional material with a given pre-programmed strain field and use that as a fabrication method for making colloidal electronic devices? So this, give rise to what we call autoperforation or automatic perforation of two-dimensional materials, which uses a preformed strain field to guide brittle fracture within a given material. So the way to do it is actually quite simple. You take one layer of two-dimensional material, and you can print using inkjet printer an array of polymeric dots on top. Each of these dots, let's say, is about 10 microns to hundreds of microns in size. And you can dry your dot, take another layer of 2D material, and just overlay on top. You form this sandwiched array structure. Now, of course, you can freely choose whatever two-dimensional material you use to form the top layer and the bottom layer. So you can make graphene encapsulated arrays, MOS2 encapsulated arrays, hexagonal boron nitride encapsulated arrays, or you can mix and match, making Janus layers. So what would happen now if you put this whole thing inside a lift-off solvent to erode away all the polymeric support for these 2D materials? Now, if you think on the scale of a single layer of 2D material folding over one particle, what would happen is that as this layer of two-dimensional material folds over this polymeric pillar that we have previously printed, you naturally form this ring of maximum hoop strain. This is very similar to the process in which you fold a piece of tablecloth over a circularly shaped table. You're naturally going to be getting maximum strain on the edge of the table, right? So this strain, this maximum ring of maximum hoop strain will actually, according to Griffith Theory, can be used to attract a randomly generated crack within the material, and the crack will propagate along this ring of maximum hoop strain. So experimentally, this is very similar to what we can predict in theory. Basically, what happens is that anywhere there's no support of the 2D material, it will fracture. It will actually, you will see the propagation of the crack will follow the edge of the circular pillar that we print. And then as a result, you get this perfectly punched out particles that are flanked on top and bottom with the 2 layers of 2D material, just like a dumpling or a ravioli, depending on where you come from in the world. But this is the kind of sandwich structure that we can make using this kind of auto-perforation method. Okay, so this is actually a beautiful picture that was taken by our colleagues Felice Frankel inside her studio, where you can see this stripe that you see is actually the lift-off solvent, this mechanical shockwave that we create to generate the initial seed crack, or to nucleate the seed cracks. You can see the crack starts to form on top of this shockwave, and then later on, the process you already see on the previous slide, it starts to propagate and cut across the circularly shaped pattern, form these colloidal electronic devices. So we're not doing anything crazy here. All we're making is basically this 2D membrane encapsulated composite. But of course, by using different ink that we print using our inkjet printer, we can control whatever composite that we're making inside this dumpling. So by controlling the ink volume, we can tune the size of our colloidal electronic devices down to roughly the size of a human red blood cell. We can also control the shape and morphology of this little thing that we print by using different inks with different viscosity and surface tension. You can actually make them to look like a human red blood cell with this colloidal shape. By using nano magnetic particles inside the ink that we use to print, you can actually make the particles magnetic, and then you can control its local motion using an external magnetic field. You can control its flipping, its rotation, and translation. But I think the fun part here is that you can actually control whatever 2D material you use to make on the top and the bottom of this dumpling that we're making. You can, for example, control the optical property of the particle by mix and match different, optical responsive 2D material. For example, in this case, we're making either a graphene particle, a MOS2 particle, or a hybrid Janus particle with one layer of MOS2 on top and one layer of graphene on the bottom. It, of course, will have different photoluminescence and other optical properties. The even more fun part is that, chemically, with 2 layers of defined 2D material on top and bottom, you actually have chemical access to 4 surfaces because each layer of 2D material have its internal phase and external phase, right? So you can actually, using our fabrication method, control the either covalently or non-covalently what kind of functional groups you can fabricate. You can adhere to the surfaces of these different layers of 2D materials. By doing so, we can control the mechanical flexibility of our particle. You can make them strong enough that it will stay sort of in this pancake shape, or you can roll them up into a burrito or like a taco shell. These particles can be made strong enough that they will be strong enough to survive a nebulization process in which they are aerosolized from their native liquid state into aerosol particles and travel across the room and be landed onto a glass slide for future electronic testing, right? So this can actually travel as aerosol particles. So here are the things that we can do with these particles. But what about electronic features? So if you think about the structure of the particle, it's very simple. It's got a dumpling shape. So there are 2 electronic modes, predominantly 2 electronic modes within the particle. One is the in-plane mode that you can make into a very simple chemical resistor, something that will switch its resistivity based on the chemical it touched. So here, what we can do is with the same graphene particle, we can selectively adhere onto the surface an amine functional group, which will grab onto the gold nanoparticle inside groundwater. So this becomes a like heavy metal nanoparticle sensor within groundwater. So by dispersing the particle into the groundwater and then harvest them back afterwards, you can measure the conductivity change of its surface, and this is very selective and sensitive. On the other hand, if you use something that's called a nitrile triacetic acid ligand, or NTA ligand, using the same chemistry, you can functionalize the same particle with a different ligand. Now this suddenly becomes a zinc sensor, a zinc cation sensor. So here, what we did was that we put, again, magnetic nanoparticles inside the ink that we print the particle. Hence, the particle becomes magnetic. These little magnets will traverse through a soil matrix. When it comes out on the other end, you can use a strong magnet to harvest them back onto your, inside your microfluidic stage, and then later on tested under a probe station. So to cut the long story short, these can be made into very sensitive and selective chemical sensors using its chemical resistivity of the 2-dimensional materials. I think a more fun part of this kind of the geometry of our particles is actually in the cross-plane domain. So imagine, right, you have this particle, let's say if you make them with graphene, then from top to bottom, you basically have this 2-terminal device where you have an electrode, a graphene electrode, another layer of graphene. In the middle, you can print whatever you want inside that polymeric gel that you use to make the particle core. So in this case, what we're doing is to make them into a MEM-resistive device. I think last week there's a tremendously insightful talk on MEM-resist devices. We're not doing anything special here. All we're doing is printing black phosphorus nanoflakes, which is a known MEM-resistive material, inside our polymeric gel to form these kind of pathways, MEM-resistive pathways from top to bottom. And if you look at its electronic behavior, all we're doing here is that within a particle, then this allows us to build a particle that can be switched on with a positive voltage. So this is a reversible, non-volatile memory, 2-terminal memory, and this memory can be swapped back to its non-conductive state. We're using a negative voltage. So one of the things that we did with this particle is that giving one single particle, we can actually make them into a 15-bit random access memory. In this one particle that you see and the color that you see is basically vertical conductivity, we can program in the letters MIP with the vertical conductivity, and you can read it out and erase it later and do it all over again. So I think at this point, I'll just sort of switch gears a little bit, and because now with the autoperforation, this allows us to make electronic particles. But if we take a step back and think about what are we doing with these colloidal electronic devices? Certainly, we're not anywhere close in making these devices into computers that can run Microsoft Word, for example, right? So, but I'll show you this. For me, I really like this image, and I know for some of you might find it disturbing, which I apologize. But this is the idea where a group of army ants can come together and form a bridge across a crevice. So I think this really resonates with me in terms of the vision of colloidal electronic devices, in that maybe in one day we can have these very tiny little electronic devices and do computation and other things in a distributed way, in that different entities can come together, and when accessing the collective behavior or the emergent behavior about our little sort of useless entities, we can access a tremendous function that none of these individuals can perform by themselves. So our group is working, in this direction in terms of accessing, communication and different kind of collective behavior between these particles. One of the critical things that we have to solve before doing that, though, is locomotion, active locomotion. How does each one particle can access active locomotion at its own will? Right, so that I'm not talking about passive locomotion where you have these particles just flow freely within an embedding medium, but how do you access active locomotion? And so this is actually also compatible with our autoperforation fabrication technology. So here, what I'm showing is basically, instead of just doing this very simple sandwich structure of graphene or 2D material polymer graphene, you can actually modify this fabrication a little bit using what is known as a carboxymethylcellulose, or CMC. This is a water-soluble polymer. So if you print this instead of the usual polystyrene or other polymeric material, we can create a fabrication method that allow us to pattern these microwells within our PMMA underwater dissolution. So these microwells are basically 10 microns in diameter and maybe 100 nanometer thin, followed by the surface profile that you see here. So what this microwell allow us to do then is to create a fabrication methodology where we can use electroplating to electroplate different kind of metals on top within the microwell, because graphene, for example, is conductive. So we can use electroplating to do this. As you can see, the platinum that we chose to electroplate within the microwell then it appears to be this dark color. So if you follow through the fabrication, add this step onto our original autoperforation fabrication, you can basically make particles that are after the autoperforation process will give rise to this Janus platinum layer on top of the original sandwiched structure. So this additional metal layer allows us to do something a little bit unusual, which is just to when you put the particles inside of a hydrogen peroxide bath, then the platinum can be used as a catalyst to decompose hydrogen peroxide into these oxygen bubbles that allows these particles to generate these bubbles and propel themselves to move. So this is just a step in the active locomotion direction, in which, again, we're borrowing knowledges from the colloidal science community, and we're introducing it onto our colloidal electronic devices to make them perhaps a little bit more useful than they are today. So I think I'm reaching the end of this talk, and I'll just summarize what basically I have talked about today. We take a colloidal particle, and you can think of two-dimensional materials as origami papers, and you can fold them around this colloidal particle, and this method basically gives rise to a bottom-up defect self-assembly method, which we can then use as a controlled fabrication method. What I didn't get into today, but it was covered several weeks ago in the same MIT.nano seminar by our postdoc, Volo Coleman. He has basically extended on the idea of using two-dimensional material to create nanoelectronic circuitry to make a active solar cell in the form of a photodiode integrated with a chemical resistor that you heard a little bit about today, and also a memory resistive device on top of a single particle. Now this actually three-device circuitry allow us to to access logistical computing in its most elementary form. So I think 2D material research in a very real way can be slingshotted by this particle, colloidal particle that is stuck in the middle into a new direction, which allow us to extend artificial electronic devices into previously inaccessible locations and environments. So of course, as I alluded to before, that there are lots of other problems that we need to tackle before colloidal electronics will become useful in any way, shape, or form. So we have talked about today the integration of nanoelectronic sensor and memory in the form of two-dimensional material on top of this 10 micron size particle. But of course, we have to worry about how do you power these particles actively, right? So we can have photovoltaic or other traditional ways like RF signaling, these radio frequency energy transfer. But it turns out none of these traditional energy harvesting methods scales very well into the microscopic regime. So, efforts has to be made on thinking about other ways that can augment the energy harvesting for colloidal electronic devices for them to be useful in the future. And of course, we have to think about ways in which we couple these two devices together. How do we communicate from one particle to the other? And then how do we utilize the fact that they can move by themselves and they can communicate with each other to form larger order assembly or perhaps dynamic assembly of these individual colloidal devices to form the basis of future sort of distributed computing using colloidal electronic ensembles. And these are actually topics that have sort of touched upon within my thesis. So I'll take this opportunity to advertise for my thesis defense on next Monday, in which I will talk about basically all 4 points. But today, we obviously only have time to discuss autoperforation as a fabrication technology that can integrate sensing and memory with the form factor of a two-dimensional material. So with that, I'll thank the people that have contributed tremendously into the work that you have heard about today. And I just want to highlight that the fact that the work that you heard about today was an effort that is under the SMURI grant between Mike and Tomas it was actually an effort led by Tomas in the EUCS department. And if you're interested in the details of the study that I have talked about today, feel free to check out the November issue of Nature Materials last year, which covers our work. Thank you very much for your attention, and I'll take any questions if there's any. Thank you.
Thank you, Albert. That was amazing. You have indeed painted a whole new vista of what might be possible through hands-on nanoscale, I guess the way I would portray it. There are so many different ways of putting together all these different nano elements. And indeed, you showed us that through inkjet printing, 2D material handling, and then very clever appreciation of cracking down on nanoscale, you're able to indeed generate these nanoscale, micron scale particles and then actually electrically activate them. In so many ways, I feel like you have generated an ability for us to rethink how to handle the nanoscale and kind of open a whole new set of projects that this can lead to. So thank you for that.
Thank you for saying that. I really appreciate it. Yeah.
My pleasure. I'm going to start asking you some questions. I have received a couple on the chat. Of course, I have a bunch of questions I want to ask you about as well. But just to let all of the others who have tuned in know, please, now's the time to send chat with questions, or alternatively to raise your hand, and I will call upon you to make sure that indeed you have a chance to be heard and ask a question appropriately. So let me start by investigating the Griffith's autoperforation law that you indeed introduced. The question is, the actual way of breaking the sheet is by providing a pulse or maybe a beat of pulses that will cause the breakage eventually. Is there any dependence on the frequency of the beat of pulses, if that is chosen as a choice of how to fracture?
Yeah, I think that's an excellent question, and indeed we have not actually studied how this the frequency of the pulse, how does that correlate with the fracture? But if indeed you're using a mechanical wave to generate that initial nucleation of the defect, so to speak, then I would naively think that the higher frequency that you have chosen would then correspond to maybe more fracturation. And indeed, if you don't do this well enough, then the 2D material can crack on top of the particle, which is what you don't want, right? So I think it's a careful balance about the initial density of the nucleation of the crack, and should let them freely travel at their own will to explore the sort of strain energy landscape that we have created by the underlying particles that we have printed. And yeah. So.
I'll ask you one more, a related question, although I suspect the answer to it, which is, the Griffith law, again, provides you the guidance on how to understand what parameters you have. The Young's modulus, the strain, every one of those guides you. The one thing clearly that one can ask is, well, is there such a thing as a Young's modulus in a molecule to molecule or atom to atom kind of bond that a graphene sheet has? Is it rational to talk about it as Young's modulus? And maybe it is, given the fact you have hundreds of atoms, not two atoms working with each other to generate such a behavior. I assume when you dial in your cracking, it is done experimentally, and hence all of the parameters kind of are lumped together, and you're really just using the Griffith law as a guide, right?
Yes, of course. Yeah, there are lots of sort of fitting parameters that we have to use in order to explain some of the experimental observations that we found. Of course, as you mentioned, Vladimir, there is a concept of Young's modulus within graphene, right? And people have measured it, perhaps varying a lot based on how your graphene was. Was it exfoliated? Was it liquid exfoliated? Was it CVD grown? And if it's CVD grown, what is the defect density? And all of these factors will factor into the Young's modulus consideration. But yeah, no, of course you're right that this Griffith guiding theory was one of the models that you can in fact use to rationalize the programmability of controlled fracture. And it seems simple enough, at least for a non-mechanical mind that I can understand. It's an easy enough theory. I know there's a lot of further variations of the Griffith theory later on, but this initial seminal paper published in 1921 was one that I was able to appreciate and utilize to explain some of the experimental phenomena. But yeah. Thanks for that.
Well, of course. Let me just move to the actual applications that you observed. You observed the memristor behavior, and you found it is programmable by choosing different pulse. You didn't necessarily spend too much time telling us how did you program and then erase your memristor. That's one question. And the second question would be, how long is the memory duration? How long does the mechanical compression stay?
Right. Again, two excellent questions. I think the mechanism at which the memory resistance turn for black phosphorus material is, I think, at the current stage is being understood as this interfacial memory resistance pathway in which we have this oxygen defects that can electromigrate within the pathways that we have created using our printing method. The first question was on
first of all, how do you erase it and write it?
So you erase, basically, so what happens, so you erase it with a negative voltage. So this is reversible memory resistance. And basically what happens in our experiment is that you can, first of all, land the particle onto a platform and then program in your memory, and then you can lift it off by dissolving away whatever is underneath it, and then you capture it again afterwards, and then you can read out the information that is stored in the vertical electronic memory that are protected again by the two layers of graphene within the black phosphorus material. And if you want to switch off the memory, you just run a negative voltage shown by this voltage characteristic curve here. So in our experience, the memory resistance, to answer the second question, the memory resistance is actually quite stable. So it's non-volatile. I have obviously not tracked the memory resistance to its failure, but it can stay there for days on out without really a decrease. And one of the reasons is that we have to bear in mind that our memory resistance pathway across the particle, this dimension is at least 1 micron in length. So this is quite a long pathway, meaning that you actually have to spend more energy than these nanoscale, for example, TiO2, or these very small nanoscopic memory resist devices that people use for neuromorphic computing. So the switching time is obviously not comparable. But the advantage of that is actually it's quite stable, right? So once it's turned over, it takes a lot of effort for you to then drive back the oxygen defects in the reverse direction. And so it's quite stable in our testing. Yeah.
The top and the bottom electrode of your MEM resistor are graphene, correct?
Yes, yeah. So and we used ITO as the bottom sort of electrode, and graphene sits on top, and the tungsten probe just directly come down and contact the graphene on top. Yes. And
you're counting on a high series resistance, lateral resistance of graphene, so
exactly.
that you only write a small spot under your probe.
Right. So it turns out, you don't want to go much more above this switching of voltage, right? And then because of the lateral high resistivity, sort of sheet resistance within the graphene, when it's fabricated in this form, you actually do not. It turns out the spreading current is in such a way that you don't really affect the adjacent pathway by that much. Yeah. But of course, that if you want even better tunability of these digits, one simple way is just to fabricate contact pads of different metallic contact pads, which then our later on work of fabricating of electroplating electrodes, smaller electrodes on top of the graphene can also be utilized for that kind of application, in order to access even more stable digits and bits of memory.
As one of the last images you showed us was the one of these particles swimming through H2O2, propelled by the emission of oxygen in a process. The way you're powering this is by optically, or how are you?
No, yes, this is a chemical powering scheme, right? So I think self-power is sort of a misnomer, but the idea is that this is an old scheme, again, not invented by us. Platinum is known to catalyze the decomposition of hydrogen peroxide, right? So hydrogen peroxide is the chemical bath that this particle is sitting in, sort of analogous to how biological cells are always sitting in a glucose bath, which utilize glucose as the chemical energy input. So the particle here harvests the chemical energy within the environment, turn that over into oxygen bubble, which then mechanically impact the system to propel it forward.
I guess if I'm going to imagine my solar opportunity here would be to use your inkjet printer to print a polymer blend that would be solar active and generate 1.25 volts, let's say.
Right, and you can make the oxygen and the hydrogen bubble, and that'll be doubly fast, I guess. Yeah.
And if you shine on the left, you can go to the right, and if you shine on the right, you would
exactly
go on the right, and you can have a steering mechanism.
Right. Right.
It's a remarkable technology. I'll ask the very last question here that came through the chat, which is, what is the closest commercialization application that you might imagine this discovery might lead to?
Right, yeah, so I think the closest sort of entry point to the market for technologies like this are perhaps still in its sensing ability and the ability to remember stuff, right? So one of the critical challenges of, let's say, being able to detect something and remember, even maybe as a function of time, is tremendously hard with existing technology for small scale systems, right? Because if you look at how ingestible electronics or other centimeter scale or modes or these type of millimeter scale devices are currently doing it, you always do real-time information feedback, either through Bluetooth or optical. So this is a real-time information feedback. And that becomes less and less likely at the micron scale, because the energy efficiency is just low for, if you want to make an LED at high inefficiency, it's tremendously hard. And also the light it generates probably does not penetrate through the soil matrix or skin or what have you. So one way of, sort of dealing with that problem is just to remember what you have seen. And perhaps then you can store the information digitally, and then later on, when the particles do come out, you'll read it out. So in that sense, you can think about, you know, a wide array of commercialization possibility. For example, could you use this as sort of like particles that you can put into oil wells for exploration of oil and gas industry? Could you think about maybe detecting a chemical nutrient within a soil matrix, or, you know, through microfluidic reactors for instead of installing millions of little sensors alongside these microscopic reactors that people are building for sort of these production on demand chemical industry, you can just simply, you know, throttle in a little particle or a group of particles and making them into chemical sensors that are that can record the information, which you can use the information to back out what is going on within your small scale reactor system. Yeah, so I think there are lots of different ways where people can apply this technology to great effect, even within the next few years. Yeah.
And of course, you inspired many of us to imagine additional technical achievements in the lab that this kind of technology can lead us to. So thank you again, Albert. It's been a truly fantastic talk. I can't but just be in awe of what our graduate students and soon-to-be doctors indeed are able to achieve in their time at MIT. So thank you again for treating us to your work. With that, I will just remind you that you should join us again this coming Thursday at 11 o'clock. We'll have a talk on fast and energy efficient monocolor depth estimation on embedded systems. This is by Diana Worf, and I very much hope that you'll have a chance to join us for that. But till then, thank you for joining us today. We'll see you.
See you. Thank you for the invitation.